So I'm a theorist, so most of the thing I'm going to talk about will be based on, not only based on the facts, but also on my own science fiction that I enjoy writing and publishing. Okay. But also, so most of the things I'm going to talk about will be based on my own vision and also science fictions. Okay. All right, so the topics are, first of all, where are we today in particle physics? And also, where are we heading to with the future collider? In terms of physics targets and goals. What are targets and goals? And for what, right? In order by reaching those targets and goals, what kind of questions can we answer and what kind of questions do we want to answer? And how? What kind of physics and technology can we utilize and shall we utilize? Right? But I'm going to rearrange these questions, and I'm going to first try to address what questions do we want to answer and do we have to answer? And in order to answer that, what do we have to do with the future colliders? And what do we need in future colliders? What kind of capabilities and functionalities do we need to answer that? And eventually, with those capabilities, how well can we answer those questions? And maybe future collider may not be able to answer all questions fully, satisfactorily. So there may be something else we need. So what else do we need to complement future colliders? Okay, so these are topics that I'm going to address today. But again, I'm not a super expert. I had to learn many things in the last few days by looking at the online talks, official documents, having a conversation with my colleagues. So many things will be incomplete based on my own vision. And here are many other experts. So if you have other opinions or better explanations, please feel free to bring them up. Okay. All right, so our journey all starts with the Higgs boson. So we have the Higgs boson, but it's not a random, just one of the many particles, right? It is the Higgs boson, which generates the masses of all the elementary particles that we see. So it uniquely shapes our daily life. If the Higgs boson's properties were slightly different, that would change the masses of elementary particles, size of the atoms, maybe more, and our daily life would have been totally different. Right? Even our existence might not have been guaranteed. So we really want to understand why Higgs boson has these particular properties. Right? And there could be many other questions to answer, but at least we have this Higgs boson, and we have to study this as well as we can. Right? So here's one of my favorite slides. Without a ball, we cannot score, but we do have a ball today, which is the Higgs boson. So let's study Higgs boson as well as we can. So that's the post-Higgsism and start of a future collider vision. All right, and also the discovery of the Higgs boson makes many questions more real and more solvable. For example, why do we exist as we do today? It could have been very philosophical and conceptual question, but we do have the Higgs boson with particular properties. So this question becomes more real and questions that we have to really answer. And we have more tools to answer these questions. First of all, Higgs boson, our existence depends a lot on the evolution history of the universe and the Higgs properties. So we are so eager to see the early universe. For example, what's here in the Big Bang and how did the universe evolve? What causes that? All those questions are relevant to why do we exist as we do today. And Higgs boson can help us answer these questions. Higgs is not just one single particle. Higgs can open up whole new ways to see and understand the universe. Every time we see something with the new wavelength, we learn something new. So different wavelengths carry different information. So in that sense, Higgs is a new wavelength of our observation of the universe. Okay. So how does that work? So Higgs potential, for example, has evolved for a long time with the evolution of the universe. But at some low temperature, if the second minima becomes the global minima, phase transition happens, and Higgs mechanism is triggered, and masses are generated, structures that we see are all formed. Right? But interestingly, the evolution starts from the Big Bang energy scale, which is much, much larger than the subatomic energy scale that Higgs mechanism happened. So this very, very long evolution makes the Higgs potential today and Higgs properties today very sensitive to the initial condition of the early universe and evolution history of the early universe. So by measuring the Higgs potential today and its energy dependence a little bit, by extrapolating to higher energies, maybe we might be able to get some hints of the early universe physics. So this big sensitivity makes the Higgs boson a great telescope of the early universe. But also, that introduces most difficult problems in QFT. That sensitivity is actually huge, and we have to answer this question. Why Higgs phase transition happens so late, and why is the Higgs boson so much lighter than the Planck scale? So these are not theoretical, conceptual questions anymore. We have the light Higgs boson. This is a real question we have to answer. And it has been the most important driving force of particle physics for many decades, LHC, future collider, etc. But with the discovery of the Higgs boson and nothing else, this question became more puzzling, more difficult, maybe most difficult problem nowadays. Maybe we need to reformulate space-time concepts and its connection with the quantum mechanics and relativity. We may need new ideas, breakthrough new ideas. Okay. So in all, we want to know what causes the electroweak symmetry breaking at such a low energy scale. What's going on behind the Higgs boson and its phase transition? What's going on in the early universe? Right? So that's the beginning of the journey. And future collider will help us answer that. So these are the physics targets listed by European strategy from Future Circular Collider Working Group. You can see those lists in this website, recently published it. So among the 8 physics targets, 4 of them are related to this question, right? And that's going to be the part 1 of my talk. Okay. So I'm going to start with Higgs boson, with the future collider. So what do we do with the Higgs boson, after all? So let's understand the Higgs properties as well as we can. In particular, we have already measured many of the Higgs couplings to other particles. So at present, most of those couplings are measured at 10% level. But with future colliders, maybe we can measure about 1% level or sub-percent level. And there could be small deviation in those couplings from the standard model predictions. Then that means something new physics, right? So that's the first direction we can take, of course. But here's one exception, which is the Higgs self-coupling, which is the coupling between Higgs bosons by themselves. We haven't been able to measure this Higgs self-coupling so far. But with future colliders, we hope to be able to measure this Higgs self-coupling at about percent level accuracy. But this Higgs self-coupling is so much important parameter because that determines the shape of the Higgs potential, so must be related to the Higgs phase transition physics. So we have to measure Higgs self-coupling in order to know what's going on behind the phase transition. So here's a cartoon showing what we know and what we want to know. So from the discovery of the Higgs boson and its mass, we know the location of the minimum and the curvature nearby it. But we don't know the remaining shape of the potential. Okay. But we want to measure the remaining shape of the potential and its energy dependence a little bit, then we can know the early universe physics and phase transition history. So in order to do that, the immediate next variable we have to measure is the triple derivative of the potential, which is the triple Higgs coupling, the coupling between 3 Higgs bosons. Okay. By measuring that triple Higgs coupling, we can know a large part of the remaining shape, and we can do some more understanding. All right, so how do we measure those triple Higgs coupling? So here's how we usually think about triple Higgs measurements. So upper 2 plots show the expected precision on the lambda triple Higgs coupling from these collider processes, okay, as a function of lambda itself. Okay. So what they actually measure at Future Collider is the cross-sections of these processes and interpret the expected precision on those cross-sections as a precision on the lambda, because those processes depend on the lambda. Okay? So this might be good enough if the only our goal is to test the standard model, and if the measurement it agrees with the standard model prediction, it's good. Otherwise, there's something new, right? But if there's a deviation, that means there's a new physics that we don't know. So not only lambda, but also many other contributions will be non-standard model, which is very, very model dependent. So in those cases where there's a deviation, in order to really measure the Higgs potential, we need to know what other non-standard model contribution exists, and we need to be able to distinguish Higgs potential contribution from all the other contributions. But they are all very model dependent and must be a very complicated job. Right? But we need to do that in order to measure the Higgs potential. And also, there could be non-standard model coupling structures, not just modifying the standard model coupling values itself. For example, Higgs coupling to WW and ZZ, this is a serious problem. So this first term is the coupling structure that exists in the standard model. But this second term doesn't exist in the standard model. But new physics can definitely induce this new coupling structure. Then we have to introduce this new coupling structure as well. Those are not only affecting the cross-section differently, but also have a different energy dependence. So they are really different couplings and different physics. Okay. So how are we going to do that? And how are we going to extract the Higgs potential model independently? So I'm going to focus on this particular process that produces two Higgs boson and Z boson through the triple Higgs coupling from the E plus E minus lepton collider. Okay. So I'm going to address challenges and the methods how to do that using this channel. And I'm going to use effective field theory as a model-independent setup to describe many, many new physics models. Assuming those new physics are heavy, this effective field theory description can be valid in many, many cases. Okay. So that means I'm going to introduce higher dimensional effective operators in addition to the standard model Lagrangians in order to capture those new physics effects. And among many, many dimension 6 operators, higher dimensional operators, this operator that consists of 6 Higgs fields will contribute to the Higgs potential and triple Higgs measurement. Okay? So this C6 coefficient is something that we want to measure. But again, there are many other operators that can contribute to the same process. For example, I can list the 10 dimension 6 operators that consist of at least one Higgs boson or electroweak gauge boson and consist only of Higgs boson, electroweak gauge bosons, and electrons. They have a potential to contribute those Z Higgs process. And indeed, all 10 operators contribute in somehow. So in order to really measure this previous diagram and distinguish them from all this, we need some work. Right? So how am I going to do that? So here comes many other observables and parameters. We need to combine precision measurements of the electroweak observables, triple gauge couplings, and all the other Higgs properties. Okay. All these measurements can constrain all the irrelevant contributions to the Z Higgs independently from C6 measurements. Okay. So no single measurement and no single collider can do this job. We need multiple observations, measurements, and colliders maybe. So what kind of future colliders can we think of and proposed actually? So E plus E minus collider, there are two major categories. One is circular collider and the other is linear collider. So these two are circular colliders. They usually have a total higher luminosity but cannot go up to high energy. Linear collider shown here, ILC and CLIC, have a relatively low luminosity, but can go up to higher energy, and also have a handle about the polarization of the beam. Using the polarization, we can utilize the angular distribution to know coupling structures better. Right. And FCCEE, Future Circular Collider, is European one, and CEPC, Chinese one, Circular Collider. C may or may not stand for Chinese, right? Right. And ILC is Japanese one. CLIC is another European one. But C doesn't stand for circular, right? It stands for compact. Okay? So again, CLIC is a linear collider that is proposed to build up on the LHC site. A few tens of kilometers can go up to 3 TeV collision energy, something like that. Okay? And another important type of collider is Hadron-Hadron collider. So HH means Hadron-Hadron collider, because this is the type of collider that we already have, LHC, right? And we have a good plan to upgrade the LHC with the high luminosity setup. It's almost approved already. And by upgrading magnets to 16 Tesla using the same 27 kilometer ring, we can crank energy up to 27 TeV. That's LHC high energy version. And in the far future, we're going to build a 100 kilometer, much bigger ring with the 16 Tesla magnets. Then we can crank energy up to 100 TeV. Okay. So these are major Hadron-Hadron collider that is proposed in the market.
Do you know the status of HE?
Sorry, HE, yeah, sounds good. So I listed here. I'm not going to talk about it today, but EH collider is useful to measure the proton internal structure, right? Proton distribution function, etc. So anyway, here's the list of all the proposed major future colliders. Okay, some details. But CDR is recently available for LHC projects, Future Circular Collider projects, and also CEPC. And technical design report has been published for ILC. So the techniques and physics studies are most mature for ILC case. Okay. All right, and also it's interesting to compare different capabilities of different colliders. So focusing on the E plus E minus lepton collider, there are three major capabilities. One is polarization. I told you that linear collider can handle the polarization of the E plus E minus beam. And energy, linear collider can go up to higher energy. And circular collider can have a generally larger luminosity. So I'm going to compare these capabilities in terms of expected precision on the Higgs coupling and various cross-section measurements, etc. So many numbers, but basically what we concluded from this comparison is that any capability is good enough, I mean similarly good. For example, polarization can handle angular distribution and can give us more information. But higher luminosity shown here without polarization can compensate that deficit. Okay. So from this comparison, our conclusion was that the best collider that we can build would be something that we can build, something that we have. Right? Anything will be good. But there's also important caveats. By combining all these capabilities and by having measurements and multiple energies, we can get synergies in addition to these single measurements. Okay? So let me illustrate that using the final results. So here's a theoretical prediction on the cross-section Z Higgs Higgs compared to the standard model value. So one is standard model, and the second term C6 is the one that we want to measure. And indeed, there are many other non-standard model contributions. Okay. But by combining existing data at the LHC and lab, and assuming ILC 500 GB data only, we can achieve only 28% on the C6. But previously, I told you that we hope to be able to measure C6 or Higgs potential at person level. So it sounds pretty difficult. And what's the cause of that? from this expression, we can see that many other unwanted operators contribute with the much larger coefficients. The one we want to measure comes with 0.056, but other unwanted operators come with much larger coefficients. That's one of the main causes of the difficulty. Okay.
Just a very quick question.
Yeah.
So those numbers come from on-shell conditions?
On-shell condition, what do you mean by on-shell? Sorry?
Those numbers in terms of the Wilson coefficient?
Wilson coefficient.
Are they fixed in the all energy?
Yeah, we haven't considered the loop correction. It's a tree-level calculation. Yeah. All right.
Oh, sorry, why go after the C6?
Sorry?
I mean, it looks like C6 is going to be very, very difficult. I understand the physics.
Yes.
But I mean, if you measure any of these others,
Exactly.
new physics as
Yeah,
well,
exactly. That's what I'm going to say.
To focus on these?
Right. In order to measure C6 at percent level, we need to measure everything else at
You
0.01%.
need to find new physics before you actually get.
Yes, exactly, exactly. That's the strategy that we're going to take, actually. We can constrain all the other coefficients from other previous measurements and data, right? But anyway, before we, yeah.
So what percent are these known to? These, I mean, CWW and CHL?
Sorry, what percent of what, sorry?
How well do we know, are they constrained?
At the moment, I'm not sure. We have already always combined existing data and future data, so I don't know. But we can reach down to 0.01% level by combining many other things. Okay, so before I get to that numbers, let me tell you why we have such a large coefficients only for this. Okay. Because those are from a contact interaction that gives coupling structure that doesn't exist in the standard model. And contact interaction, usually contributions grow with the energy, S over mg square. So those contributions are enhanced by S over mg square, which is already order 100 at 500 GeV collider. So in order to measure such effects and distinguish them from other effects that doesn't grow with the energy, we need to combine multiple energy data. Okay. That's one strategy we're going to take. Okay. So again, in order to measure C6 at 1% level, we need to measure all these at much better precision. And lab electric precision is only marginally at this level. So surprisingly, we always believed that electric precision at the lab was very, very good enough, but it's not actually in order to measure C6 at percent level. We need to improve electric precision even more. Okay. All right, so by combining not only 500 GeV data, but also 250 GeV data and more parameters, we can reach 5% uncertainty for C6. Okay. We can better constrain all these parameters. Okay? So this roughly shows that we need multiple energy setup and many, many different observables. All right, so no single measurement, no single collider can do all. All right, as an aside, let me quickly tell you about the top measurements. Top might be the second most important particle that we want to measure, right? Its mass is close to the Higgs web. It could be coincidence, or there could be something interesting. So we want to measure top very well. And here are two plots that we usually think about top measurements. We measure top by direct top production, but that requires large collision energy, at least 2 MT, which is 350 GeV, right? But circular collider may not be able to get there, etc. But interestingly, top can affect Higgs and electric precision observable that I have been talking about through the loop corrections. So it will be small, suppressed by loop effects, but it can be the leading top effect, right? So some operators and RG mixing of the operators, etc. And through that, our preliminary results show that all those top operators can be somewhat constrained without direct top productions, only indirectly from Higgs plus electric precision observable. Okay. This might be some interesting direction we can take. But also that implies that top effects through the loop is not negligible in the Higgs precision. Right? We need to take into account these top effects in order to reliably measure the Higgs properties, right? So important messages too. All right, so any questions so far? All right, good, let me move on. So part 2 is more on the Hadron-Hadron Collider, dark matter and direct discoveries. Not only the Higgs boson, we have many other reasons to search for new physics. But still, most important motivation for direct discovery is naturalness candidates for the Higgs mass. Supersymmetry and warped extra dimension, composite Higgs, they all can explain why the Higgs boson is relatively light. Okay. SUSY and fermions chirality combine to protect the scalar masses. And in the warped extra dimension, for the projective Planck scale is exponentially small. Or Higgs is a composite particle, but composite scale is relatively low. So each of these explanation is based on symmetry or some dynamics, and all predict some new particles beyond the standard model. Okay. So far, I always say that new particles are predicted just beyond the standard model, but maybe today I have to say not far beyond the standard model. We haven't discovered anything so far. But if we believe naturalness, there must be something new, and there will be something not far beyond the standard model. That's why we want to do some direct discovery by going up to very high energies. Right. So energy frontier targets are those colored particles in supersymmetry, composite Higgs models. And also, they also predict good WIMP dark matter candidates, such as pure Rho, Higgsino. They are important candidates that we have to test. But in those high energy regime, Higgsino becomes a very special particle. Okay, I'm going to elaborate this more soon. But partly because Higgsino is the partner of the Higgs boson, our main character today. Okay, so Higgsino becomes special. And there could be or may not be boundary of the naturalness philosophy and argument. Okay. So colored particle direct searches, gluinos, quarks, or some partners could be directly produced, and they can decay to standard model and LSP, missing energy, with large energy and momentum. So the signature will be standard model particles and missing energy with large momentum. So at 100 TeV collider, eventually the reach goes up to about 10 TeV, okay, for a stop case. But interestingly, those direct searches are not so much sensitive to this compressed region where the stop and its decay product's mass spectrum is more or less degenerate. Okay? Energy of the produced particle may not be energetic enough. So interestingly, in this region, resonance searches can be possible. Resonance searches are very unusual and unfamiliar for supersymmetry and composite Higgs, etc., because those models usually predict R or T parity, which is kind of a discrete parity that distinguishes standard model and its partner particles. Okay. So any heavy new particles will decay to at least one LSP, which will be missing energy. So resonance reconstruction is difficult. But still, in this compressed region, directly produced particle has a long lifetime, which is suppressed by small phase space. And they can form a colored bound state. For example, stop and anti-stop pair produce, but they decay slowly, so they can form a colored bound state called the stoponium, which is a spin zero particle having the same quantum number as the Higgs boson. So this stoponium can consequently decay to a diphoton, exactly as the Higgs boson decays to diphoton. But more precisely, stoponium pair annihilates to diphoton. Anyway, then we can construct diphoton resonance at the 2m stop. So there will be very clean and easy searches. So those resonance searches of SUSY can cover these compressed regions very reliably, unambiguously. Okay. So it's one interesting direction we can take. Also, non-colored particles, such as Winos and Higgsino, can be a dark matter candidates. They can be full thermal dark matter, They have a small coupling to the standard model particles, so they can be in a thermal bath in the early universe. And their relative density today depends on the dark matter masses, and they grow more or less linearly with the dark matter mass. But happen to be 3 TeV pure Reno and 1 TeV pure Higgsino can be the full thermal dark matter. And heavier ones predict too much relative density, so it's more or less excluded. But lighter one can still be some subdominant dark matter. So it's very important to test these two ideas up to this mass range. And that's not possible at current LHC, but will be possible with future colliders. For example, disappearing track searches at 100 TeV can cover these regions. Okay, so it's very important to test this simple idea of a dark matter. Okay. All right, and in general, electroweak particles can be also pair produced through the Drell-Yan diagrams, and they can again decay to standard model and missing energy with large energy momentum. We can do a searches, but search results depend sensitively on many other parameters. For example, in SUSY, tangent beta, the sign of the mass parameter, mu parameter, etc. Even though second heavy particles are relatively heavy, we naively think that they will be decoupled and all these parameters are essentially meaningless. But actually, the small mixing between lighter state of particles and heavier state of particles is still very important. Okay. So interpretation of data in terms of those theory parameters depend on many other parameters, complicated. And simplified model approach does not apply here. So we need to be careful when we use the simplified model. But that's the case for the we know. But for the Higgsinos, we don't have such problem. At high energy, Goldstone equivalence theorem of the Higgs boson is inherited to the Higgsinos. But there are two sets of nearly degenerate neutral Higgsinos. So this inherit is only partial to each Higgsino. Each neutral Higgsino is partially satisfying Goldstone equivalence theorem. But what we observe is not a single each Higgsino effect. Some of those two Higgsino effects, they are not distinguishable. And that observable satisfies the full Goldstone equivalence theorem. So Higgsino always decays to Z boson and Higgs boson equally. Okay. There's no complicated parameter dependence anymore. Each Higgsino may depend on those parameters sensitively, but what we observe as a whole doesn't depend on that. So collider phenomenology is simplified, and one plot is enough, and simplified model could be applied to here. And we can know whether what we saw is the Higgsino or Renos or Venos. So it's an interesting physics, and it's essentially due to that electroweak symmetry is effectively restored at high energy. Right. All right, also Higgs has more surprises. Higgs may have heavier partners, but they do not always show up as a resonance peak. They can show up as a resonance dips or nothingness. Even though there is a particle and resonance, we don't see them. Right? It's a theoretical prediction, not experimental resolution smeared. Right? That's not a science fiction. That becomes very generic phenomena in the SUSY, MSSM. So here's a plot showing what kind of resonance shape do we achieve in the heavy Higgs masses versus tangent beta parameter. In all this region of the MSSM, there's no pure Higgs peak. And in this green region, we do have pure dip. And in this red region, we don't see any resonance, even though there is a heavy Higgs resonance. So this phenomena becomes very generic. And we also understood why this phenomena didn't happen previously, but will be very generic in the future. Okay. This is basically due to the shadow scattering from complex interference. The attenuation of the forward-going wave is related to the imaginary part of the forward scattering amplitude, attenuation. But that imaginary part is produced from the Kukuski cut when the mass of the Higgs boson is greater than the 2MT, the top particle running in the loop, right? So if this kinematic condition is satisfied, Higgs production from the gluon fusion will have imaginary part, and that can produce shadow scattering and resonance dip or nothingness. So in the high energy region, where we search for heavy Higgs, this phenomena could be very generic. All right, so resonance searches has to be modified. So our main motivation was the naturalness. Can there be naturalness boundary? When do we give up naturalness, right? No definite answer. Someone already gave up, but someone will never give up. So we may need breakthrough new ideas to solve a naturalness problem or something. All right, lastly, complementary probes. So here's a sentence from a Future Circular Collider CDR report. No experiment at colliders or otherwise can probe the full range of dark matter masses, etc. No single measurement can do all, again. And Future Collider might not be able to answer all these questions that I posed in the beginning. So we may need multi-messenger or interdisciplinary probes, such as from cosmological, astrophysical, dark matter direct detection, neutrinos, axion, flavor, deep learning, gravitational wave. We need to combine all those approaches. We need to be open to many other things. And also, big science approach and passions are needed. We need to build something big in order to answer that, in order to do something. And I'm sure there are a lot of exciting opportunities ahead of us. So we need to do something. We cannot just sit down and wait for something to happen. Okay? So this is all I prepared today.
I have one question.
Yeah.
In Suji, okay, for example, the scar particle,
Yeah.
as far as I remember, the current limit is about okay, 2 tag something.
2 tip, yeah.
And then you go up to the 10 tag
Mhm.
with the 100 tag,
Mm-hmm.
central mass energy,
Mhm.
the 3 Hadron, right? Okay, most Hadron. Then, is that there is no any limit of the mass of each
Right,
part?
right. It could be as high as we want.
You do think,
Right.
but some other people does not think also.
Well, that could be related to naturalness argument.
Yeah, that's right.
Right.
That's right. So,
But theoretically, there's no upper
So-
limit.
in a way, if you go up to the 10 tab, in principle, if you go up to the, the 100 tab,
Yeah.
that's not persuasion.
Right, right. So there's no any guarantee of discovery.
Do you remember a few years ago when the Higgs was found? Okay,
Mhm, mhm.
People were, some of Suzy people were really exciting
Mhm.
because star quark
Mhm.
was bottom quark,
Mhm.
maybe very, very light.
Yeah,
Okay,
yeah.
but it's not. Turns out
Right.
it's not within 6 months.
Right.
Okay, they goes up to the. They start with the 500 jet,
Mm-hmm.
1 tab, 1.5 within 2 years.
Yeah.
So it's like there's no any criterion.
Right.
So
Yeah, there's no any guarantee.
10 tab,
Yeah, there's no any guarantee, as I said. Right. So Hitoshi Murayama usually argues that we don't know where the new particle is. So let's start with the precision machine and get some indirect hints of the new physics energy scale, and let's just target that energy scale. That's what happened in the lab and LHC, right? So yeah, it's a difficult time of particle physics, so we need new ideas, new motivation.
Is this other is more than twice the top mass?
Yeah.
There is no resonance involved. What would be the other handles that you can add to experimentally observe that? Is there no different with that model, or how can we see this?
So
Is
your
there other way than looking for resonance? What would be
so your question is, if this happens,
Yes.
is there any other ways to
what
look
would be
for?
other handles to discover that?
Right, that's a good question. Actually, heavy Higgs doesn't decay only to, for example, top pair here. Right? It can decay. It could be produced with TT bar heavy Higgs, and it could decay to something else. So there are other channels that are not affected by this phenomena. So there can be complementary searches.
Could you go to the page where you discussed the polarization?
Here.
Okay. So
Okay.
it seems now that the realistic ILC would be 250, not 350.
Right. So this first column is based on 250. Yeah, with polarization. Yeah.
100% or what percentage?
80%, 20%, something like that. Yeah. And second one is without polarization, but at higher energy. Yeah.
So I guess now that at the LHC, among the experimentalists, there's a lot of interest in long-lived particles. And
That's
even,
right.
I think, a proposal for Methuselah
Exactly.
experiment
Yeah.
to measure particles outside of the detector. So
Right.
maybe, I don't know if you can comment on that.
Right. I have also worked on those projects, and I was thinking whether I need to put them in, but I thought it's not really the future collider things. I didn't put them in.
Well, maybe it's
Well-
a question for how detectors are designed and
Right.
how triggers are made. Do these types of things need to be considered?
Right. That's a good question, but I don't have an opinion, and I don't have a really good expertise on detector details. But indeed, many theorists are interested in what kind of detectors we need to build, what kind of capabilities we need, etc. Michael Paskian also had a long paper on it, but I personally don't know much about it.
Any other questions?
So what is supporting for the future collider, in your opinion? Of
Oh.
course, you cannot do nothing, right? You can choose, barely choose only at most one, right?
Right.
If you're
What are you
taking-
choosing?
you do nothing.
I don't know. Sorry.
What are you choosing?
Something most easy, right? ILC might be the most ahead, then I would choose ILC. I don't know.
So any other question to Sunghoon as well as also to Mark? Or please just talk.
Mark, the detector looks like a good deal. Detector looks like a good deal. Relatively, should we say.
Okay, if you don't have any further questions or comments, let's close the session and thank you.